Okay. Okay. So again, let's continue with the EV charger. So usually in the first page, I'd like to ask you about the question between AC and DC charger. So just now we say DC charger mean the input is DC, AC charger mean input is AC. And then we also know that the power level usually will be DC charger will be much higher power level. And usually the power level can at least 50 kilowatt up to 200 kilowatt. Now then the charge is really high power. Because we talk about rapid charging, half an hour. So for instance, many of the Tesla vehicle will be something like 100 kilowatt hour. So that means if you want to go for half an hour, finish the charging, 200 kilowatt power. So the power level getting quite high. But there's many famous international standards for EV charging. I think you can name a few. For instance, there's a number of IEC standard. We also Tesla its own standard. We also GB standard. GB from mainland China. We also Japanese standard, CHAdeMO. They're all really famous standard nowadays. So you can see that in the US, Europe, China, and Japan, they're all big organization, big company have the EV system and also EV charger. So how long it takes to a full charge? Of course, we know that if you use 1C, then that will be, say, 1 hour. If 2C will be half an hour. So for rapid charging, we're talking about 30 minutes would be best. And of course, gradually, many people like to go for even shorter time, say 15 minutes. But I think we did a calculation. We know that if we want higher power, so that means we need higher power of the power electronics, the charger, the system getting really big, expensive. We do also need high current. You can see that we want to focus all the energy within, say, 50 minutes or 30 minutes or maybe 5 minutes to push it to a battery. So of course, we need a high current, high Coulomb in order to do that. So in this case, the only thing we do will be we need to increase the power electronic size, increase the power source from distribution. But usually, many distribution system like PG&E may not able to give you such a high power anyway. So you may need to have a long application. You may need to see if that location have suitable power line for you. So that's many things uncertain. So I think we all know that for different mode of charging, we have CC mode, constant current mode, CV mode. We also have trickle charging, but it's basically got 3 types of the charging method. Of course, there will be more than that, but basically CC will be important, also the CV. And for GE charging, what type of GE charging mostly common use? Of course, all the chargers should implement with the constant current mode charging, CC mode. Next question will ask, what is the efficiency for the charging? Anybody can tell me, what do you think about the performance of the charger, performance of the battery? What do you think about the charger efficiency? Maybe from our power line, charge it to the battery, from the power line down to the battery, what is the efficiency?
95.
At least 95. Today, all the power electronic is at least 95 so that you can able to sell, so that you can publish piece of paper. If your paper, trying to publish paper, you say your charge only 80%, nobody will accept your paper. So at least you need to perform in at least 95. I mean, 90 is not good at all. 90 is okay 10 years ago, maybe 20 years ago, but today 95 will be a norm. Next, about the efficiency of the battery. What do you think the battery efficiency? We're not talking about the charger, but just the battery. Charge in, charge out, that one trip efficiency, how much it is?
25 plus?
So how much?
25 plus?
95?
Plus?
More than that, I think.
Around 98, 99%.
Yeah, something like that. 90, 99 would be more reasonable. You can see that today the efficiency of battery is really good now. I think if you look about some paper, maybe 20 years ago, we are talking about, say, 90% or something like that, 90, 95, but now we're at close to 99, 98. Round trip efficiency. I mean, they perform really good. That's why when you charge the battery, most of the time you can see that the thermal management may not be too critical unless you're using rapid charging. You see, if you're using standard charging, for example, like 0.2C, it takes 5 hours. So if a battery, EV battery, say 50 kilowatt hour, then in 0.2C, talking about the efficiency, the power will be 10 kilowatt. Then even the 5% power losses, that will be something like 500 watt. That was still too much anyway. And then if your battery charging system goes up to, say, 2C of charging, 100 kilowatt, then you can say 1 to 2% will be already 2 kilowatt. It's such a huge power. So today, the battery itself already opposed to 98, 99. Together with the charger, maybe 5% loss. And together with the validity charge, we got a few percent loss. So totally round trip efficiency opposed something between, say, 95 to about 90. So if anybody tell you their round trip efficiency only 85, that's wrong. We can't afford such power losses. Power performance is important. We now try to move up the curve to 95, maybe more than that. So that means the charger 95 still need to have improvement. Some of the good charger talking about 97 for the power electronic efficiency. And then the inverter 97. So we round trip efficiency got 3% in charging, 3% in the discharging, totally 6%, plus the efficiency of battery 1%, so totally 7% of the round trip efficiency power loss. So that would be much, much better than all the gasoline vehicle. So that's why you can see that the charging efficiency is now doing really well. So if you try to do some survey for some journal paper, you can see that 20 years ago, they talk about the efficiency only about 90, 80 something, but now they all go up to 90 something. This is more reasonable. We need to do that because the battery size is so big, we cannot afford to have 1 or 2% power loss. And then how can we reduce the charging time? I think the only thing we can do will be to push more current, right? High power, high C of charging, high C rate. So that all depend on the charger itself and also the battery. So that's to say, even though how good your charger is, but when you plug your charger into your vehicle, the vehicle BMS will talk to the charger and say, I can only accept a certain amount of the current. So doesn't mean you can inject too much. So there are communication to say, now we are using 1C or 2C, whatever. And in many vehicles, you can also adjust the charging current, charging rate. For instance, like Tesla, you can also adjust the charging current. So that's something we can also do. Why we need to do that? Because for many household garage, if you want to connect with charger, your household may not have sufficient power source. So that means you need to adjust your current to be lower current so that you are able to charge in your own household. If too high current, then you trip your panel. Especially many charger, they not have a really good filter in the front end. They may draw some pulsational current. So that may trip your system. So that's why the charging time actually are affected by many scenarios. Then next question will be, what's the disadvantage to increase the charging time, charging current? Of course, we know that expensive, cost, thermal management, size. The charger will be too big, probably bigger than your car. I don't think you like that. Even though the charging cable, I think you know that all the cable, the copper can only stand for about, say, 5 amp per amp square. So if too high current, 100 amp, 200 amp, 300 amp, that means you need to have a really thick cable. So that means it's too heavy, impossible. Today you can see that they are really thin because some of the chargers, they not only have good copper, but also have some cooling. You can see that in the future, if we go for really high power charging, we need to have some cooling in the cable. So that's something we're looking for. Lastly, or most important would be safety, charger safety. Later on, we'll discuss briefly about the charger, why safety is so important. Any question up to this point? So by the end of this chapter, you should be able to answer properly of all these questions. So today we're going to discuss a few things. Firstly, we talk about some introduction and then talk about some basic component in a charger. And then next will be AC charging and DC charging. And then we go for the charging safety, or the safety, and also some standard and also internal structure. That's what we're trying to cover. So, I mean, basic concept of charger will be, we convert AC, probably usually all the power source today are AC. Then we convert them into the battery voltage, which DC. So the main is now AC. So most of the converter we're trying to use today for EV charging must be AC to DC converter. Then the speed of the charging certainly will highly depend on the power level for the charger. If your charger will high power enough, and then the C rate of the capacity of the battery. If the C rate is low, then of course you cannot use rapid charging. The AC source is an issue because we may not have sufficient power distribution capability. So many of the locations we cannot install high power charger. So that's also one of the restrictions why today the charging network is not well developed. You can see that if you want to buy an EV, you're looking for everywhere you can charge your EV similar to you fill up your vehicle by gasoline. But on the campus, we don't have that many charging stations. And some charging stations may not be rapid charging. In case you have some kind of the urgent issue, you need to rapid charge your vehicle within 15 minutes, you may have a problem. Some of the rapid charging, they charge really expensive. I think today the electricity price roughly about, say, 40 cents per kilowatt hour, depending on the location. But for rapid charging, they may charge 3 times. Why is that? They need to pay for their facility. When you go to a rapid charger, not only the thing you saw there is only a connection. They got big charger behind the machine, which is really big, really expensive, like the charger circuit we developed. And then they also have a big transformer to transform the PG&E voltage to the charge voltage. So that means just the transformer also really big, very expensive. So that's why to install a kind of rapid charger, the price we're talking about could be at least, say, 200,000, this kind of pricing. Yeah, really expensive. Yeah, if including the foundation, the facility, that could be even more. So that's why it all become the issue, why we don't have sufficient charger and why the user may not be like to buy an EV because they don't find sufficient charging station. So the key question for this chapter will be, we have the CC mode, CV mode, we have mentioned many times, constant current mode and constant voltage. So why do we need to use the CC mode? I think we mentioned that briefly. Maybe you can tell me why we need to use CC mode.
CC mode normally when it is charging, so we set the mode into CC mode. So that current remain constant until it reaches to a certain voltage, so that then once it reaches to we say 80%, then we set it to CV, constant voltage, so that voltage remain constant and current may expand between them.
Yeah, that's the process. That's the feature we can see from the curve, how the CC and CV mode look like. But why we need to program the CC mode in the beginning? Why we need to do that? Why don't we program CV mode in the beginning? Why most charger, they dedicated must have the CC mode?
Just to get the enough supply of power. Let's start.
Yeah. Okay. What else?
Because after a state of charge, the efficiency of the battery to take the power reduces with a constant current. So we need a constant voltage, or what was the last one called? Drip method?
Trickle charge.
Trickle charge, yeah. For the last 7% charging.
Okay. And well, later on we discuss why we need to use CC mode. Yeah. And then also, do you think EV fire are highly related to the charging? I think we occasionally can hear quite a few EV on fire, right? But have you heard about which case would be more often? during the charging, during the motoring, or parking, idling, which charge will be higher? That's according to, we don't have to answer this, but we can look up from the statistic. Many cases, we may not know the answer, but the statistic will tell us which is the more likely the answer. What do you think? Which one? Charging, motoring, or parking? Parking means idling in terms of the vehicle, right? Which
About the accidents.
about the fire accident, not the traffic accident, but fire.
Oh,
Fire charging.
During charging.
Okay, what do you think?
Charging.
Charging, how about me?
I believe charging.
How about, okay, there will be some, yeah, you're right, charging much higher charge, but we'll tell you why next. And then, of course, because in this chapter, we also discuss about the basic component for charger. So we need to know about what it is. In the future, when you want to develop your charger, there's something you can do. You see, charger business is really good. Firstly, if you want to develop your next business, if you want to manufacture EV, it's too late. The people has been doing it for the last 20 years, and the investment is too much. But charger is much lower cost for investment. And there's a many charger demand everywhere. So that means you need to investment, but it's really popular, really important, high demand. So your next business, after my class, you may think about to set up a charging station in different locations here. Then that will be really good business. You can see that we have really high demand. In the future, I'm not quite sure which vehicle will be the winner, but EV must be one of the winner. So that means when we need more EV, then we need more charging station. At the moment, we don't have charging station. So that's a really good business. So you don't need high investment. If I ask you to manufacture an EV, design your own EV, too expensive. You take a few billion or multi-billion to set up a new company. You may not be able to catch up with the rest of the large enterprise like Tesla, BYD. You can't beat them. But charger is simple. Basically, power electronics, much easier to do that. So my recommendation is think about your future business after you graduate. Charging station. Okay, simple, easy, and big money. So next thing will be, that's why you need to study the power electronics. So today I only give you 1 week or 2 week lecture on charger, but charger is a big topic. So in the past, when I was in my former university, I just spent the whole year to talk about only charger for one single topic. So, and then we also like to see how we're going to design a charger. Of course, we don't put too much detail in here, just give you some basic principle how we design a charger, how we're going to calculate the charging time. So that's how we're going to take away from this lecture. So firstly, why CC mode? Mainly about efficiency. The constant current allows more effective transfer energy to the battery. Then mainly about the battery chemicals. The chemical or battery, they prefer a constant Coulomb, constant current to do the energy transfer inside the chemical reaction. So that will produce higher efficiency. So for battery, why we now have 99% of efficiency? Because we use CC mode. If you use CV mode, the efficiency is much poor. So CC mode is the best chemical reaction for the battery to have high efficiency. So that's why we do that. So all the charger must have a CC mode, unless those lousy charger without any control. So for battery health point of view, CC mode actually can help us to maintain the nighttime, the lifespan, to maintain overall battery health. So then we can also monitor the control the heating effect. So the battery health most critical part is the temperature. So we need to examine that, make sure the temperature will be suitable. And constant current mode, current is in a way is more proportional to the temperature. That's another way you can, regulate the temperature really well with the constant current mode. You see, with a chargers like that, even though you tell it using CC mode, say 100 amp, but when the BMS detect high temperature, you communicate with charger, say now we're too high temperature, you reduce the current until the current become more comfortable. Yeah, so that's how you could try to do. So mainly about the chemical reaction, which is make the constant current drive will be more stable. So that's why we do prefer CC mode. Maybe some lousy charger only a constant voltage. Now you got a power supply you with certain voltage, 5 volt. If your 5 volt USB directly connect to the battery, you can still charge, but that's not constant current mode. Constant voltage, then you don't know what kind of current behavior. Current sometimes can be high, sometimes can be low, sometimes can be unstable. That may damage the battery. So overall, we need constant current mode. And for fast charging, because we use constant current to directly inject out the Coulomb I and T product to the battery. So that's why we're able to deliver much higher rate, intended rate of the charging. We can also calculate charging time much easier by using CC mode. CV mode, we can't really calculate because we are not quite sure of the current. The impedance of the battery is vary with the state of charge, state of health, temperature, everything. So if just instead constant voltage, you're not quite sure what kind of current inject to the battery. So you cannot calculate, you cannot estimate when you're going to complete the charging. But so CC mode, we know because we know how much AH we inject to the battery. So in this case, we can much better to control the charging system. Of course, for the safety. And as constant current mode, we are able to control current voltage properly. We also prevent the overcharging. Overcharging usually means the overcurrent, overvoltage to the system. So that would be help us with the safety. So that's to say, battery protection is the first. For any charger, besides the charging time, everything, we need to ensure that the battery will be under protected. Safety will main concern. And voltage regulation, then we can use constant current mode to control it, and then later on move on to the CV mode to finish the charging. That's a better way to regulate the voltage. And we can therefore regulate the state of charge more properly with the CC mode. So that's everybody like to do that. And later on, we'll switch from CC mode to CV mode. In this case, we can therefore regulate the current. And the EV approach to the end of the charging, then we change the CV mode. We can therefore, during that time, the current will be much, much lower. Then we can able to inject a final charge to the EV system. And the battery design and the power electronic design also really highly related to each other. So we tend to use power electronic design to control CC and CV mode, make sure that we got high power drive and effective power drive. Key thing would be chemical aspect. Near the end of charge, then we know that we cannot inject too high current. You can see that near the end of charge, the impedance of the battery already quite high. Quite high, and then you try to inject more current, then current time impedance is equal to the voltage you want to inject. So you need to increase the voltage so much in order to inject more current. That will be too high demand for the charger. So at the end of the charging, the charger will be suffered so much. So you do need to change into CV mode. So we're just using constant current. No matter how high impedance is the battery, since the voltage is fixed, then we know how much current we're going to get into the battery system. That will be much safer for the battery, much safer for the charger. And then, more importantly, we know that about the accident, fire accident. According to statistics, we found that most of EV fire or more likely happen during the charging. So something quite interesting. I think a few points we can look into that, why that thing could happen. In the charging, of course, heat will be built up. Although we just now we say the efficiency will be 99%, 98%, so little energy will be there. But however, charging during that time, the vehicle will be idling, not moving. So we don't have any natural cooling, air circulation around the vehicle. So in this case, especially when vehicle under the sunlight not covered really well, then the heat buildup will be quite quickly. Your vehicle usually is a car park, indoor, jammed next to each other. When you park your vehicle there for charging, next vehicle also charging, all the vehicle are charging, heat will generate. That could cause some higher risk of the fire. And also, If the vehicle under the motoring, of course, we know that the vehicle are moving, all the sensors will be on board properly. So when they detect anything, they will alert the driver, alert the VCU system. But in the parking, the driver already gone, so nobody to take care. So in this case, the risk will be much higher anyway. But anyway, for the statistic, we found that is something we do see that EV fire will be more important or more often happen. So to summarize, I can see that mainly the heat build up during the charging, especially under the sunlight or high temperature is some issue. And also equipment. You see the charger usually being used by many, many people. Your EV only used by you or maybe your family, but EV charger system are used by everybody. Every time when charging station, there may be more than 20 users are using the EV. So that means connection, maintenance, cable, everything is uncertain. You may not able to have a good maintenance for the charging system. So that means you also involve external component, and maintenance will be an issue. And also BMS, battery management system. The battery management system is able to help us to control the battery, make sure it's safe. But however, during the overcharging in some particular cell, if the BMS is not able to balance it, that may be a big problem. You see, when we use fast charging, you talk about 30 minutes we will fully charge the vehicle. But I think for the last lecture, we mentioned about BMS calculation. When we want to balance it, depend on the balance resistor or balance MOSFET. Usually design for BMS, they don't want to involve too high power for the BMS electronics. So the electronics are quite light low. So they cannot manage with fast charging and balancing. If charging 100 amp, if you want to equalize each of the cell, you can't use best way 100 amp to balance all the rest of the cell, but you can't. You only use 5% or 10% of the current. So you may not have sufficient time to equalize all the cell if the cell is not doing really well, especially for some aged vehicle or some BMS not designed properly. So that's why the BMS is one of the issues which may not able to catch up with the rapid charging. So that means you can see that from the statistic usually will be medium charging or maybe fast charging, rapid charging have more chance for the failure. But so at home in your own garage, probably you can think about using standard charging, low speed charging. That would be good enough. So here is an example. For example, like just happened a few months ago in San Francisco, EV charger at their house. So all on fire during the charging. So by statistic, having EV charging are more problematic than a vehicle driving on road. So EV fire will be something we need to take care of. But however, from the statistics, we know that EV on fire will much less than gasoline vehicle. You compare them in here, for 100,000 EV being shown, only 25 reported. But if you compare the gasoline vehicle, will be 1,005. So of course, the gasoline vehicle on fire will much more higher chance anyway. So EV is still safe. You're talking about nearly 100 times safer. So I think that's why I'm not discouraging anything. I actually encourage you to use EV. Although you have fire, but the chance will be 100 times less. So why not to use EV? And EV fire is less common, but however, it's more problematic to extinguish. Very difficult to put it off. So I think mainly about EV itself have an internal energy. Even to put out the fire, it's still able to reignite. Many cases, I think the EV reignition is quite common. So that means an EV, we know that after the fire being extinguished, then we still need to put the EV under monitoring for quite a few days. Make sure no EV surrounding them within 50 meters. If you burn the EV to a scrapyard, you cannot put any EV next to it within 50 meters. That's the safety standard. And then you need to use the cool down the vehicle. The best way is to put the whole EV under water to cool down. So we don't care about the short circuit anymore because the battery already damaged. And also the EV on fire will be a lot of problem because there are more than hundreds of the chemical emitted that can be including chemical, a lot of chemical, a lot of carbon monoxide, hydrogen cyanide, and also heavy metal. So that means EV on fire is really dangerous. Don't try to go nearby it. You must have a lot of protection. And control EV fire also take a long time. You can't just say using CO2 extinguishers. I don't think it works. Using water probably not working. From the statistics, we know that for EV, we need something look like more than 3,000 gallons of water continuously to pour on the vehicle to cool down. So a lot of water. Only little bit of water, no use. But you need to go away. So a lot of the water. So that's the issue for the fire anyway. But anyway, let's look how that's only the introduction to tell you how important is the charging. So we need to design really good charger for EV in order to eliminate all the risk. I think in the future, if we do have a second course for EV, we have a second course to talk about more advanced topic for electric vehicle. Then we can focus more on the EV fire. That will be really a special topic, really getting more important. So basically the EV charger, you can see that the major component here, including the first thing you can see the AC to DC converter. We convert AC from a power point here into DC voltage. The DC voltage will be the voltage going to connect to the battery. But between them, we have another electronics there, including some coupling inductor to control the coupling. That can be coupling inductor can be help us to increase voltage or decrease voltage, or sometime on wireless power transfer charging system, we use coupling inductor to transfer the power through the air. And then we can also use conductive, like the circuit we show you some time ago, buck converter, boost converter, buck boost converter, many other converter can do the job. And then that will connect to the battery system. Many cases, the battery system, we call it battery pack, will also come in parallel with some super capacitor pack. So two of them are working together, and they all require DC charging. So you can see that AC DC converter, if we go for the DC charger, basically from the DC side, it goes into the battery. So in here, you've got DC converter to convert the DC voltage. So DC and AC charger mainly about the input side. So now that you can see that. So firstly, we have AC DC converter from the main to so-called rectifier become DC. And then we do have a DC converter to monitor and regulate the voltage, including the conductive charger or wireless charger. We still need that for monitoring. So for the charger control, then we need to use it to control the current and control voltage. So that's a very typical way we can regulate the CC mode, CV mode, or trickle charging. So output stage, so that usually will be DC voltage connect directly to the battery. And even though for the AC charger, then the output usually will be from the AC side. You can see that outside on the campus, we do have some kind of the medium charger called the AC charger. The input is AC, and then you put in a wire, put into your vehicle, and then that plug output still AC. They not yet change into DC yet. So that means all the medium charger you see everywhere on the market, their charger is not a charger. It's only a cable connection. The cable connection will give you the wiring for the AC wiring, plus some communication. So that means those AC charger, the whole thing are AC. They did not convert anything into DC yet. Only DC charger, they will convert the DC and plug into a vehicle. So that means theoretically, the AC charger is not a charger, it's only an AC wiring connection. So other supporting things, including you have some display to show you the state of charge, how much you're going to pay, how the connection and the pin number, something like that, and then some communication to communicate between the EV and also your charging station. So that's basically how a charger should look like. For the voltage, Typically, EV voltage will be from 200 to 600. But some low power EV can be as low as 48 volt. Some new EV will be 800 volt, maybe even higher. But you can see that many vehicles are also so-called the EV, including the forklift, golf car, and wheelchair. There are also a small motor, small battery there. The voltage vary from 12 volt, 24, 36 volt. Sometimes can go up to 48 as well. And then for the charging standard, you can see that we are for single phase AC, then we have about 120 volt, maybe 100 volt in Japan, 220 volt in China. In UK will be 230. So of course, in here, some locations 108. Then for the three phase, then we know that the power can be 208 volt, 240, maybe 480, depend on which level you're going to look into. And for Japan, we got 220, 400, and 440. In China, 380. In UK will be 400. So you can see that the voltage are quite varied. But that's quite okay. For charger, we are usually the design will accept variable input voltage. They call power electronics there. So the input voltage, they don't care too much about it. So usually when you buy a charger, you can use in multiple locations because the input voltage are quite flexible. And for all the chargers, they usually implement with the current mode and voltage mode into the system. Then we all know the charger, we also separate them into DC charging and also AC charging. AC charging and DC charging, and each one of them, they can be also conductive and wireless. Conductive, that means all the chargers we are seeing today. Wireless, we don't have such international. We have international standard. We don't have any commercial vehicle here. The thing is, wireless charger, we require both the vehicle and the charging level to be wireless. So that means you can see that we got a couple of coil, couple of inductor, one receiver, one transmitter. The transmitter embedded inside the charging station, maybe the ground, and another coil receiver embedded near the bottom of the vehicle. So the thing is, today, all the vehicles are designed using conductive charger. So at the moment, we don't have any major manufacturer producing any wireless yet. Maybe after a few years, there may be. But today, we only all doing some kind of laboratory testing. We don't have any commercial development yet. But we have been working so much on the wireless anyway. So the wireless charger, just like a transformer. You know, transformer, we can transform voltage or transform the current. But the transformer, we are using a magnetic core. But then a wireless charger, just like a coreless transformer without any core. So just like two coils, it's still a transformer, but between them, we don't have any magnetic ferrite or magnetic iron. And then the separation will be somewhere a little bit further away, at least 10 centimeter to 20 centimeter, depending on the standard and the location. But even though we are separate them, then of course the coupling depend on manufacturer, depend on dimension, depend on coil design. We like to have good coupling between them. But so the coupling coefficient cannot be 0.99, probably only about 0.2, 0.3, depending on your coil arrangement. But that means the wireless power transfer efficiency may not be too good anyway. But however, I think wireless power transfer mainly to aim for simple, easy, and convenient. So that means if you want to drive your EV to a parking lot, you don't need to plug in and unplug. It's automatically you can charge. Just like your phone charging today, we do have a embedded coil behind it, then we can very easy to charge your phone. So that's how the concept. So you can see that for the charging control, the charger usually will be conducted by a DC to DC power converter. We use a two loop. One is a current loop. The current loop is an inside loop, inner loop, current control loop. So that's the most popular constant current mode charging can be like that. Another loop would be voltage loop, just to control voltage. Voltage loop will control the CV mode. Inner loop will control the C mode. Input side, then we can either accept DC input or AC input through a rectifier. So the basic configuration for EV charging schematic Then you can see that we have the CC mode and CV mode. Then all the charger, when we started, usually start from the CC mode first. And then once it reaches to certain criteria, and then the C mode inner loop will disable, then only the outer loop, voltage loop will be enabled to continue with the charging. And then that's the basic one, but of course some of the network may also trickle charging. You may see if you want to include trickle charging control loop here, how are we going to modify the control output? You may think about it, how it can be done. Then all the terminology, I think after so many lectures, you know quite well now, including the energy content for the battery, that will be kilowatt hour, kWh. And the state of charge usually from 0% to 100%, and state of health as well, 0% to 100%. And then there's also C rate, that means how many C. So that the typical one will be 0.5 C, 1 C, and 2 C, versus another jargon for BMS battery management system. They all important terminology for the charging. So I think by today, you should all know about it. So the key component for EV, certainly you can see that we have the AC to DC converter. So that means that's one of the front-end component. We need to convert AC to DC anyway. But of course, that's a simply, you can see that rectifier. We also need to include the filter in the front. That means before the rectifier, you should have a filter to filter all the transition noise, transient noise. Because the rectifier, they rectify AC into DC, but somehow some switching current in the charging network, they may feed back in the front end. And for the charger, we don't want our charger to inject any pulsation current or harmonic in the power line, because that will not be allowed by the distribution. So that means some filter will be needed to filter some kind of the transient current. So rectifier you sell only DC to AC, AC to DC, but we do need another filter to do the job. And the DC-DC converter, you can see that we just need the DC voltage regulation to control the current inject to the battery. So that kind of converter can be stepped up or stepped down, depending on the voltage requirement. If the battery is high voltage, 800 volts, as we mentioned before, you may need a step up to increase the line voltage to higher. And this, of course, will be vice versa. Then the CC mode, we know that, and the CV mode usually perform the CV mode after the CC mode. But for some kind of the simple charger, they may only have the CV mode. And the coupled inductor is just like the cordless transformer. We usually call them inductor, we don't call them transformer, because they're not actually transforming the voltage. They really couple to each other for an inductor. The primary side, we have one inductor. The secondary side, we got another inductor. The voltage conversion may not be exactly equal to turns ratio anyway, because of the coupling is not doing really well. So that's why theoretically, we just call them coupled inductor. Here will be a major schematic diagram look like for a charger. Then you can see that we have a grid connection like using one phase or three-phase system. One phase for some low power, but for something higher power charger must be three-phase. Certainly, we have a filter to filter all the noise coming out from the back. You can see that AC convert into DC for the battery. Then in here, PFC means power factor correction. So we usually will make sure the input power factor will be more close to 1. Otherwise, you'll draw too much current from the front end. You see power factor equal to 1, I think you know that will be apparent power equal to the real power. Then the current will be also become equal, the real current equal to apparent current. We got less current. If the power factor is low, then we may need to draw more current. That is something we don't quite like, because today you know that the charger, we don't have sufficient current. So that's why we do need to have PFC to the front end to do a job. Then PFC will come out here, become a DC voltage. The DC voltage need to convert various DC voltage to the battery that we have a DC to DC converter. So basically, this DC to DC converter is to regulate the voltage, regulate current. So just like you can see the diagram, you can use this one to perform the CC mode or maybe the CV mode to do that. And then perhaps also the trickle charging. And then from here to here, of course, here is already DC. The battery will be quite straight. We do prefer have a low harmonic. It doesn't have any transient current. So that means we do this DC filter to filter current so that we're able to provide more constant current to the system. Of course, then you may ask me, how about trickle charge? Trickle charge, do we still need a filter? You see, trickle charge, we are not talking about the pulse in microsecond. It's not in nanosecond, right? The pulse is more in terms of the millisecond or second. So in this case, we still need a filter. The filter, we try to filter those microsecond, this kind of the noise. And then for millisecond, then we don't need to do that. Here will be really rough calculation how to estimate the charging time. I think you all have done it several times. Just the question is, if a battery pack is 50 kilowatt hour, 500 volt, so if 1.5 C charging current to the battery, then if the input voltage 480 volt, then what is the input current? And here power factor 0.95. So at 1.5 C, you can see that in the answer here, 50 kilowatt hour equal to 500 volt times the current. So the basic current, normal current, 100 amp. But now then, we are going to use 1.5 C, so that means this multiplied 1.5 be 150 amp. So we're going to have 150 amp charging current at 1.5 C. So what's the input voltage? So what the input current is power factor equal to 0.95. Input voltage 480. So for such a high AC power, then we have AC power equation √3 times voltage times current times power factor. And then that power level is equal to the standard power level multiplied by the C rate. Yeah. So now then we can calculate input current equal to 95 amp. Then the charging time all depends on initial state of charge and also the final state of charge. So now then we want to charge from 10% to 85%. So the actual state of charge requirement will be 0.85 minus 0.1, which is 0.75, and divided by the C rate will give us the number of hours. So that's very simple. I'm going to just show you how easy we can able to calculate the state of charge, the current requirement, or the time requirement to the charge. But that's all only in a more theoretical condition. So the CV mode and CC mode is the two we mainly talk about. And if the transition from CC to CV mode, many people like to ask, when do we start to transit from CC mode to CV mode? So many design depend on the current of the battery requirement. Many batteries that manufacturer will tend to say when the SOC approach to 80%, then the performance of battery will be degraded beyond 80%. So don't tend to work on 80%. So that means that even the charging, we tend to operate between 20% to 80%. So that's the best range. Then, so that means when the SOC approach 80%, then we usually change that into CV mode. Of course, some battery, you can go up to 85% to change the CV mode. So that's 90%. So 80%, 85% is just kind of the common number we can use it. So that is to say, to transition from CC mode to CV mode, so we have to measure the SOC until the SOC or battery go to about 80%, then we do the changes. The next thing about the CV mode, when we decide the CV mode, when the battery voltage allow charging under CV mode, when are we going to stop? When we stop charging, that means we will move on to the trickle charging. So it depends on the design. It's around 10% to 1% of the charging current. So during that time, when we use CV mode, the current is not controllable. It depends on the impedance of battery or the voltage for the charger. But we usually know that this kind of the current are much lower. 1C means 100%. Here, when we doing this kind of the voltage charging, then the current will drop to about 10% of the original. Sometimes it drop to 1%, depending on the state of charge. So that means for 1C charging, when it drop to 10% or 1%, that will be much more easier to manage, and the thermal losses come out may not be too significant anyway. Then under the CV mode, the current no longer become linear. We have no control to the current, but we know that this current is going to be exponentially decreasing. So this exponential decreasing mainly be related to the battery model, how the battery model look like. In here, we don't display to you about the equation. That will be in next level of the study. So basically, you can see that the curve will be something like that. We firstly have a constant current mode, and then later on when we go to CV mode, then there's two possibilities for the current. One will be linear decreasing, but more logical will be exponentially decreasing. Then it all depends on how the voltage look like in the battery, how the voltage source look like in the system. So these time durations are very with the battery. Sometimes you can go up to about 1 hour, half an hour to finish off with the CV mode of charging. So at end point of the CV here, this, and then people would like to answer how do we determine this endpoint? So for instance, initially we use ICC, this amount of current to charge maybe 100 amp. Then we know that once we change into CV mode, then the current will be dropping. How do we determine this point? In theory, many people say, oh, let's wait until the SOC go up to 99% or 98%, then stop and change the trickle charging. But many charger designs, they don't have to do that. They just wait until the current drop to a certain percentage of original current, they will stop. So that is not highly accurate, but that could be somewhere help us to simplify the charging system. So many charger designs, they will wait until you go down to a constant factor about 5% here, they will stop the charging. That will be easy enough. You don't really need to calculate exactly about SOC in order to determine when you stop the charging. This is one of the methodology many design have been using. So for the AC charging, then we know that we do have level 1 and level 2. I think somehow you heard about the AC charging or whatever charging, you have level 1, level 2, and level 3. And level 1 and 2 are mainly for AC charging. So that means level 1 is more fundamental. We use it in very beginning. During that time, the level 1 charging, so-called slow charging or standard charging, are mainly powered by our power point, say 108 volt or 110, depending on the location. So that means you're mainly using single phase 108 volt for the charging called level 1. Then level 1 has been designed as such. And then later on, level 2, they want to increase the power level. So level 2 must be higher voltage. Probably will be beyond 200 volt. Then you come to a problem will be in the United States, because they firstly try to name the level of charging. So they have level 1 charging come from the single phase main. So that will be 108 volt. But for other countries, like in UK, Hong Kong, China, the voltage will be 220 or around this value. So that means once they use any 220 volt, their charger level become level 2. Although their power is low, but they still call it level 2. So level 1 charger mainly mean the single phase voltage we are now using in the US, probably maybe in Japan. Japan also using 110. And then for level 2 charging, then in US that will be, we try to divide the power from high voltage. Probably will be 20 volt. And then, but because other countries are using 220 for their main, so that means other countries, if they have a standard or low power charger, we still call it level 2. So that's kind of the confusion for level 1 and level 2. I think I will more be happy to say level 1 for low power charger, level 2 for medium power charger. But however, in some countries, we still consider those 220 volt charger as a level 2 because the standard written as such. So again, I need to emphasize that AC charger is not really a charger. It only delivers AC power to EV with some facility, including the switches, some protection, and some simple control with the surrounding. So that's how we can recognize different kind of the charger. So here will be the one of the level of the charger. You can see the power of 2 kilowatt. Then you can see the plug. That is the NAND mask plug we usually have here. This one is the NEMA NEC 199 code. So all our home appliances are using this standard. And you can see that the first vehicle EV being developed, I think you can see that down to 1973, long time ago. Then their first one they developed is low power charging. They're using level 1. The voltage are divided from most of the home appliance. So that means this is our level 1 charger. So that's how they look like. So you can see level 1 charger, the power level can't be too high anyway, because level 1 charger are limited about the power level, usually limited to a 2 kilowatt. Like in your home appliance, usually the single phase charger are limited to about 2 kilowatt. But even though 2 kilowatt, you talk about 100 something amp, the current is still quite large. Talk about 16 amp of current. Then the next thing we look into about level 2. Usually level 2, we try to ask for high power. Then 108 volt is not capable to supply high power. So they need to increase the voltage. For instance, then they're using the level 2 voltage, like 200 volt and 220 volt, this kind of the voltage. So if we have a home appliance, then you want to install a charger, of course you will install level 2 charger. Then you, by your power point on the wall, 108 volt. So you need to get an electrician to get a line from your panel to get about 200 volt to connect to your charger. Again, your charger is not a charger, it's only a AC wiring connection. And give you some button for it to press, to start, and whatever. So this kind of charging, they have standard, the J1772. So that's the level 2 charger standard. So the international regulation for this kind of level 2 charger, they call it IEC 6229196. So typically they can separate into type 1 and type 2. Later on we'll talk about what type 1 and type 2. Then for type 1 is a so-called low power. The power level only up to 8 kilowatt power. So quite a low power. But they commonly to use in the US and also Japan because their type 1 very similar to the plug we are working on. But the connection to the battery side, EV side are different. So the connection we also call J1772 is the SAE standard. SAE is one of the Automotive Engineer Society, really biggest and society to look after all the vehicle and aircraft. So that's how the type 1 look like. Have a 5 connection, which you can see that 1 and 5, they are the voltage. the live voltage, AC voltage. And then number 3 is the ground. So we still need a ground cable for the earthing and for the protection. And then 4 mainly for the communication and also the control, just to communicate between the vehicle and the charger, how much current we're going to do, when are we going to stop, if the battery being fully charged up, then we need to stop it. So that's how the system shall look like. So I think you can see that many of them, but these chargers are mainly for IEC 62196. So there's quite a few of these chargers on our campus. Then we also have the 62196 international standard, more divided from Europe at the time. But I think many countries, for example, like in Hong Kong, we are also using this kind of the standard. In US, we also have a number of this kind of charging level available. And type 2 of course, then we try to increase the power level for type 2. So that type 2 will be like that. You can see that more connection. Because the power level will be higher, then we have to use 3-phase. You can see that the power level for this one, so the first one only got to 8 kilowatt, and type 2 will go up to 22 kilowatt. So once you go up the power level, then single phase not able to handle with the current and the power. You need to go for 3-phase. So in this one, you can see that the connection are like the L1, L2, L3, pin number 2, 3, 4. There are the 3-phase voltage, 3-line voltage. Number 5 is the neutral. Because sometimes some of the charging system, they do need to require to have phase voltage neutral. And the control will be 1 and 6. 1 and 6 will control. That will be used for communication with the charger to tell the charger and the EV how is the charging pattern look like. Number 7, the green in the middle, still the ground, that means in here. So you can see that you can go out, you can check after this lecture, you can see in the campus or out there in the city, what kind of charger is now available. Are they using IEC standard or what other standard they're going to use? The thing is, there's many different vehicles, they come from maybe different countries, they may have their own charging standard. So sometimes they use IEC, sometimes they use CHAdeMO Japanese standard, sometimes they use other standard. So that's quite interesting to see if we're going to install many charging connections in our charging station. We need to install quite a few so that you can meet all the different users. I think it still take more than 10 years for all the countries to unify the same standard. You can see that in the old day when we have a charger for our phone, at that time we did not unify them into today the USB charging level. It takes us about something like 20 years in order to unify all the power charger into the USB-C standard. So I think the vehicle charger will be similar. So, but the thing is, for phone will be much easier to promote using a single type of the charging system. Because phone will tend to carry them for different countries. So if we're using same kind of the charging format, that will be much more convenient. But vehicle more will be regional. We won't drive your vehicle from Europe to Asia or from Europe to the United States. So that means different countries, they can still adapt their own standard because the EV will not go across the continent. So that's why we still see that in the future, we may have a hard time to unify all the standards. But even though you can recognize this one, and this next time, tomorrow when you go out, you can look at the standard to see, oh, this is IEC 62196, you can say it. And this, after this lecture, you become engineer, you need to know. If your family, your sister asks you, oh, what kind of standard? You're studying EV, you need to say IEC standard 62196, you can say that. So that to present you are engineer. Okay. And then another major standard called GB standard. That will be the one commonly to use in mainland China. Of course, we cannot find this vehicle in here, but our course here is international course. we try to cater for everyone. So then you still need to know that so major standard in the charging system called GBT 20234. So that one will be one of the important standard in mainland China. All the vehicles, they are really similar to 62196. Similar, but not the same. You cannot plug in anyway. Because they look like the same, but they are not in the same kind of connection. I think the male and female connection are interchange. You cannot connect them. So you can see how you see GB standard 2034. They really look like IEC 16196, but they are the male and female are not compatible. Look the same. So you need to know how to distinguish that. When you take out and oh, that is the GB standard. That is European IEC standard. You need to know. So that's how you see that the male and female are different. So we still have a L1, 2, and 3 for the three-phase connection. And also we have ground connection for the earthing. And also have the neutral connection, and 6 on the control and communication. Fair enough, simple. And then just now, those are the major standard that we can see, GB standard and also European standard. And for DC charging, we also have many other standards. All the standard they, besides just now is AC, but they also have a similar DC standard for IEC and also for charter mode Japanese and also for GB. So let's revisit them to see what they have. So for the DC charging, usually for higher power must be there. So such high power, then the main will convert to DC. So the wiring, the cable we plug into the vehicle, that will become DC. The DC cable will be plugged into them. So with that, this voltage directly connect to the battery. And the regulation to control CCCV mode come from the charging station on the garage or on the parking lot. So the control is not inside the vehicle. So, but the communication between them will tell the charging network what kind of mode of charging, what's the maximum current, minimum current, is the temperature issue, anything. They will do all the communication. The reason we use DC because mainly, I think we all know that DC cable can carry more current than AC. And also the losses usually will be less. And since we're using high current, no point for us to rectify the AC and DC. Our vehicle itself mainly is trying to make it high density. So if you still put a high power charger inside the vehicle, it's nonsense. So all the vehicle, the onboard charger only really low power, just a few kilowatt. It's just like last lecture, we say about 11 kilowatt is the standard maximum power for all the onboard charger. For DC charger, talk about 100 kilowatt, 400 kilowatt, it's too big for EV. So all the charging control, charging power electronic, all on the ground, on the parking lot. So that's why this one only a wiring connected to the battery. So to do this one, we need to make sure all the DC connections are doing it really properly. They have a lot of the sizing control, the cable size control, how to make everything become effective, high efficiency. So the standard for the just now we mentioned about 62196. So they have a combo mode called the CCS, Combined Charging System mode. So later on when you see combo CCS, that means they also connected with a DC link for your charging. So in freeway, the power level can go up to 350 kilowatt power, really high power now, really good. Then they have two variations, combo 1 and combo 2. Later on, it will tell you what it is, called the abbreviation called EE and FF. So how the EE will be like that. So you see the top here, the same as IEC 62196, but they don't have AC connection because they are now become DC. So the DC have additional 2 connections here, become our DC. So this only head into easier to insert. If the 2 DC you are making fitting around, so this one will give it the earthing and the control, so they're able to tell the DC charger what kind of control you want to be, what kind of communication, and you need to also put the grounding for protection. That's how it looks like. So there, all these, the low connection, only the power in here. So this field only give you the control, everything, all the other connection keep fixing the location. There are no internal connection there. That's how they look like. So all this thing they call a combo because these two are put together, more like a combo. So the DC are on here. Okay.
So if we connect this to AC, it should also
No.
work or not?
No AC there. They mainly for DC. The AC circle there are mainly for you to fix it, to position, and also for the communication. Another FF would be for another standard that will be probably the high power. So you can see that the top, all so give you the positioning so that the model IEC 6196 Type 2. The Type 2 usually high power, so here will also give you high power. 2 DC are here, and then this three are that way to position your charger and also the communication. So this one called the CCS2. So the also combined charging system, CCS2. So you can see there's a many name you now introduce. We got the CCS2, also mean the combo 2, the abbreviation called FF. And this one, combo 1, abbreviation called EE. And then you can see it look like the Type 1 62196 Type 1. Okay, that's how we divide them. So now what you have learned then, we got 62196, look like this one. The Type 1, Type 2 will be different power level. And then when we move on DC, we're still using Type 1, Type 2 to be the shape, positioning, and the communication, but we don't use the AC too low power anyway. And then they use the DC, we do that. Once you plug in, the DC voltage directly go to the battery DC voltage. We don't need to use AC. So even a plug-in, this is not doing anything because our vehicle don't need to have AC DC together. This thing only give you DC. So that's how it works. So now then you know the major standard for IEC. So I think after this lecture, you go to our campus, you go to other parking lot to see what they are used, and let me know next lecture. So EE and FF are combo 1, combo 2. Another major standard will be Japanese standard called the CHAdeMO. Then these are simple, being popular. You can see many Japanese vehicles are using this one. So the meaning of CHAdeMO, you can see how about a cup of tea. That's how it means. So that means when you're doing charging, you can go for a tea. After come back, you can finish the charging. So CHAdeMO has been reviewed for many times. I think since 20 years ago, we have the CHAdeMO. The first major EV vehicle are manufactured by Japanese enterprise. They are also using CHAdeMO, but during that time, the power is really low, about 50 kilowatt, maybe less. But now then, because demand for high power vehicle, they gradually move on to up to 400 kilowatt. I think they keep going up anyway. So then the voltage talk about 1,000 to 400 amp. So that's widely used in Japan. I think in many countries, if they are importing the Japanese electric vehicle, they should also have CHAdeMO standard. So that is the issue. You can see that in many countries, we need to have a CHAdeMO standard, IEC standard, and also maybe Tesla standard. Later on, I talk about Tesla, maybe GB standard. Probably we have 4 of the connection. The transformer at the back is still the same, but in the front end, you got the 4 of them for your vehicle. So that's a really troublesome, I think, really inconvenient. But anyway, but in this country, mainly you can see Tesla, we got one, and then the other, we tend to use IEC standard. We don't have that many Japanese EV here yet. So mainly about IEC. The vehicle come from maybe France, come from Italy, or come from Germany, IEC. So here you can see that is the CHAdeMO standard. So how the CHAdeMO standard, right? So you do need to recognize how the CHAdeMO standard looks like that. look like four circles here. The power, 2 and 4 are the main power. And then I know the control wiring. Control wiring, actually, they divide with quite a few small ones here. Not only 2 of them, but more than that. So that is the shape. You can see that they're the charger motion. All right. Any question up to this point? This lecture only information to give you how the standard look like. I give you my thinking about why they do that, how they look like, how one to the other relate to each other. Then, of course, for the GB standard, we call it Guobiao. So GB standard also have their own DC charging, high power charging. So they are shaped also similar to 62196-3. They're very similar, but they call it BB type. Will be like that. The shape is different. It's quite the same, but the connection are quite different. Full power connection for here. So the other one will be the control 1, 2. They are the control. They usually using campus for the control. 8, 9 are the control. And then we also ground here. We also acidic power to support other control electronics. So that means the GB standard for DC fast charging 20234 is one of the major ones in use in China or all the BYD vehicle. So you need to recognize the shape. Again, the male and female are different from IEC. You can't put them in, although they look the same, but you cannot connect it. And then later on the Tesla, Tesla are using this standard. If you go to the supercharger, the Tesla will be using that. This one called the NACS, North America Charging Standard, only used by Tesla. The maximum voltage, 500 and 500 amp. You can see that the voltage level is slightly lower than chargeable by IEC standard because the battery inside the vehicle only about 450 volts. But probably in the near future, they may need to upgrade them to high voltage if you want to go for high power. But at the moment, they're still their power level. So L1, L2 is the DC connection. And then we also the ground here for connection. And then CP is control. And then also proximity to connect if they really fixed properly. Once they detect the proximity, they will release the current. That's how they look like. You can see that their head is not really big. Quite small, about that kind of size. I think you go outside to see any Tesla, the connection is not really big. But you can see that the power level, the supercharger, up to 250 kilowatt. So surprisingly, I'm not quite sure how they can manage the current and conduction losses for such good connection. But bear in mind that their contact area quite good. Not only this circle, but they are quite deep. So that means the contact area is still good. We still need a good contact area to ensure the current can able to connect between two places. If an only single point connection, then the contact system will be really large. So that's why there's some kind of mechanics here, how to ensure that the connection will be good so they're able to deliver such a high current. You see 250 kilowatt battery inside a EV like the Model X, Model Y, and like Model X, the power content will be something like 100 kilowatt hour. So that means if 250 kilowatt, less than 30 minutes, we can finish charging. So current demand will be quite large. 500 volt, you can see that the current will be huge current, hundreds of amp. So that need to conduct it through this kind of the NACS charging standard. Proximity, make sure they connect properly. If they don't connect, we don't release the power. Just a fixed position, make sure they are being put in properly. Many of them have similar facility, although you didn't say carefully here, but many of them, they will check the connection. Like here, they will check the connection here, make sure they send some current detect, make sure you already connect properly. then they will start to release the current. If they release the current and they don't put in properly, maybe it's close, not quite fixed it well, you can create a contact system. The proximity connection usually happen here, but they may not say here, they're probably embedded inside the control panel. Also, insert convention. That will make sure that confirm the connection are insert properly. They did that because such high current. For example, like our power plug here, we don't have any insert connection confirmation. We don't need to do that. Nobody care. But here, we talk about hundreds of amp, so we do need to do this kind of the proximity connection. So that's how the supercharger look like. That's how the connection look like. So now then, after the lecture, you should able to recognize what they are. So so gradually, Tesla move on to about supercharger. So because at the moment their present connection is not good enough, so that's why they move on to high current, high power anyway. So this kind of the supercharger connection, they start to look into. So they do have a DC connection in here, so that able to provide much higher power for supercharger. But for those non-supercharger, this is really small. I think much just like this kind of size, not sufficient for really supercharging. So in the next generation or coming generation, they're using supercharger. Usually I will similar to the combo, like the shape. But all these supercharger, all the Tesla can only use for the vehicle. But occasionally on the market, you can still see some adapter. If you're able to swap between the plug, sometimes will be the Tesla charger, change the IEC, or charger mode change the IEC change to charger mode. That's like you can swappable. Because in the past, we don't have that many Tesla charger. So Tesla, they use supply to you an adapter. So you can use the adapter to charge your Tesla vehicle from the IEC charging level. So this kind of the plug will be now available. If you go to Amazon, you can see some of the adapter, charge adapter, like what we did now for the home adapter. So the charging current now can be very, quite long. So you can also adjust the current to see how much current you want to charge your vehicle. That can be also adjustable. So there's a bar in here. You can actually adjust how far your charging is. If you don't see that, then they will use the standard mode for your charging. But sometimes if you think your charging station is not healthy enough, you don't have sufficient current, sometimes you find that although you can plug in, and usually your building, your panel usually trip, then you need to decrease the current so that you got less current for the charge. So that means the current will be adjustable. So because the current are changing, then your power charging also become acceptable. So that's how we happen for the Tesla charging connection. So Tesla will write that once you plug in, they will start the charging. They don't need to ask you to press any button. But that's why next thing to do will be, if we do have a large parking lot, we want to install charger. Of course, each parking lot, we like to have a charger. But the thing is, the summation for all the current certainly will be greater than the power source from PG&E. So that will be problem. We certainly don't have sufficient power from PG&E. So how are we going to manage? So the research paper, we see that we're going to install many of the load management, charger management system. So we have some kind of sharing for some critical vehicle. When the SOC is low, then we have high priority. If they pay higher for the rate, then we can give them higher priority. So many people are doing this kind of the analysis for this kind of the charging load management system. But the thing is, many of the EV may not able to give you the load control. Once you plug in, the system between the vehicle and the charger will determine what kind of the current will be needed. So we need a second level of the control to control when we have many chargers, how to manage the current delivered to each of the charging load. So that's the thing we need to do. That's the thing we need to have another control method to control if the charging output to see able to develop this kind of the charging management system. So here we have some example in different locations. So some of them you can see that some of the IEC standard, you can see that here. They usually will be a kind of the level 2 charger. They're all AC charger. So this kind of the charger are widely available because nowadays we can see them quite often in many of the parking lot. They're also quite waterproof. So usually some water raining will not be an issue. When they plug in, they are quite protective. So I think roughly the end of lecture, I think we stop here now. Do you have any question? No? I think this lecture give you an overview of all the charging system and all the charging network. So I do highly recommend you to remember a few important charging system and network so that you can say in front of your friend. You say, oh, this is IEC standard 16096. That's a charger mode. That is the NECS standard. You need to know that you have the type 1, type 2, combo 1, combo 2, EEFF, right? GB standard. So you need to know this. After this lecture, you become an EV engineer. You need to know. You need to show off your friend. You are now expert in the EV and EV charging, right? Okay. Before this lecture, do you know all that standard? Yeah. You see it, you saw it every day. You may use your EV, but you will not realize there's so many standards. Japanese, American, European, China, 4 major standards. They got AC, DC, Type 1, Type 2, combo, EEFF, many. You need to know this. All right. Okay. That's all. So see you again next week then.